Hello, welcome to today's session on the sliding window approach, a powerful algorithmic technique used to solve problems involving arrays or sequences. Today, we'll break down this method step by step, understand how it works, and see it in action using a visualizer with a practical example. We'll also explore both fixed size and variable size windows, discuss complexities, and clarify key concepts like subarrays. Let's get started. The sliding window technique is a method where we maintain a window of elements that slides over the array to solve a problem efficiently. Instead of looking at all possible subarrays or subsequences, which can be very time-consuming, we focus on a subset of elements, the window, and adjust it as we move through the array. This approach is especially useful for problems that involve finding subarrays or subsequences that satisfy a specific condition, like a fixed size, a maximum sum, or a certain property. There are two main types of sliding windows. Fixed size window. The window has a constant size, and we slide it across the array. Variable size window. The window size changes dynamically based on the problem's conditions. We'll explore both types today, starting with a fixed size window example in our visualizer, followed by a variable size window example. Before we dive into the problem, let's clarify what a subarray is. A subarray is a contiguous portion of an array. For example, if we have an array 1, 2, 3, 4, the subarrays are 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 2, 2, 3, 2, 3, 4, 3, 3, 4, and 4. Notice that subarrays must consist of consecutive elements. They can't skip elements like 1, 3 would. The sliding window approach often deals with subarrays because it leverages their contiguous nature to optimize computations. Let's consider the problem of finding the maximum sum of a subarray of size k in an array. We'll use an array of 20 numbers: 1, 4, 2, 10, 2, 3, 1, 0, 20, 5, 8, 12, 15, 18, 22, 27, 30, 25, 14, 7. Our window size k will be 4, meaning we need to find a subarray of 4 consecutive elements that gives us the largest possible sum. This is a fixed size window problem because the window size, k equals 4, doesn't change as we slide through the array. First, let's look at our array: 1, 4, 2, 10, 2, 3, 1, 0, 20, 5, 8, 12, 15, 18, 22, 27, 30, 25, 14, 7. It has 20 elements, indexed from 0 to 19. Since k equals 4, our window will always contain exactly 4 elements at a time. We'll slide this window from the start of the array to the end, calculating the sum of the elements in the window at each step, and keep track of the maximum sum we find. We start by calculating the sum of the first window. Now, let's slide the window and compute sums. Array: 1, 4, 2, 10, 2, 3, 1, 0, 20, 5, 8, 12, 15, 18, 22, 27, 30, 25, 14, 7. Starting sliding window search for maximum sum. Window size: 4. Initial window, indices 0 to 3, sum equals 17. Sliding window to indices 1 to 4, sum equals 18. New maximum sum found: 18. Sliding window to indices 2 to 5, sum equals 17. Sliding window to indices 3 to 6, sum equals 16. Sliding window to indices 4 to 7, sum equals 6. Sliding window to indices 5 to 8, sum equals 24. New maximum sum found: 24. Sliding window to indices 6 to 9, sum equals 26. New maximum sum found: 26. Sliding window to indices 7 to 10, sum equals 33. New maximum sum found: 33. Sliding window to indices 8 to 11, sum equals 45. New maximum sum found: 45. Sliding window to indices 9 to 12, sum equals 40. Sliding window to indices 10 to 13, sum equals 53. New maximum sum found: 53. Sliding window to indices 11 to 14, sum equals 67. New maximum sum found, 67. Sliding window to indices 12 to 15, sum equals 82. New maximum sum found, 82. Sliding window to indices 13 to 16, sum equals 97. New maximum sum found, 97. Sliding window to indices 14 to 17, sum equals 104. New maximum sum found, 104. Sliding window to indices 15 to 18, sum equals 96. Sliding window to indices 16 to 19, sum equals 76. Maximum sum of subarray of size 4 is 104 at indices 14 to 17. The maximum sum of a subarray of size 4 is 104, found at indices 14 to 17, elements 22, 27, 30, 25. Let's discuss the efficiency of the sliding window approach, as it's a key reason we use this technique. For a fixed size window of size k, we first compute the sum of the initial window, which takes O of k time. Then, we slide the window across the array n minus k times, where n is the array length, and each slide takes O of 1 time, because we only add and subtract one element. So, the total time is O of k plus O of n minus k equals O of n. In our example, n equals 20, k equals 4, so we perform 16 slides, but the overall complexity is O of 20 equals O of n. Without a sliding window, we'd have to compute the sum of each subarray of size k, which would take O of n times k time. For example, O of 20 times 4 equals O of 80 operations. Sliding window makes this much faster. We only store a few variables, window sum, max sum, and starting index, so the space complexity is O of 1, regardless of the array size. We don't need extra arrays or data structures. Now, let's look at a variable size sliding window example to contrast with our fixed size example. Consider the problem. Find the smallest subarray with a sum greater than or equal to a target. Let's use the same array. 1, 4, 2, 10, 2, 3, 1, 0, 20, 5, 8, 12, 15, 18, 22, 27, 30, 25, 14, 7, and set the target sum to 50. Array 1, 4, 2, 10, 2, 3, 1, 0, 20, 5, 8, 12, 15, 18, 22, 27, 30, 25, 14, 7. Target sum 50. Starting variable size sliding window search. Finding smallest subarray with sum greater than or equal to 50. Expanding. Added 1 at index 0, sum equals to 1. Expanding. Added 4 at index 1, sum equals to 5. Expanding. Added 2 at index 2, sum equals to 7. Expanding. Added 10 at index 3, sum equals to 17. Expanding. Added 2 at index 4, sum equals to 19. Expanding. Added 3 at index 5, sum equals to 22. Expanding. Added 1 at index 6, sum equals to 23. Expanding. Added 0 at index 7, sum equals to 23. Expanding. Added 20 at index 8, sum equals to 43. Expanding. Added 5 at index 9, sum equals to 48. Expanding. Added 8 at index 10, sum equals to 56. New smallest window found. Indices 0 to 10, length equals to 11, sum equals to 56. Shrinking. Removed 1 at index 0, sum equals to 55. New smallest window found. Indices 1 to 10, length equals to 10, sum equals to 55. Shrinking. Removed 4 at index 1, sum equals to 51. New smallest window found. Indices 2 to 10, length equals to 9, sum equals to 51. Shrinking. Removed 2 at index 2, sum equals to 49. Expanding. Added 12 at index 11, sum equals to 61. Shrinking. Removed 10 at index 3, sum equals to 51. New smallest window found. Indices 4 to 11, length equals to 8, sum equals to 51. Shrinking. Removed 2 at index 4, sum equals to 49. Expanding. Added 15 at index 12, sum equals to 64. Shrinking. Removed 3 at index 5, sum equals to 61. New smallest window found. Indices 6 to 12, length equals to 7, sum equals to 61. Shrinking. Removed 1 at index 6, sum equals to 60. New smallest window found. Indices 7 to 12, length equals to 6, sum equals to 60. Shrinking. Removed 0 at index 7, sum equals to 60. New smallest window found. Indices 8 to 12, length equals to 5, sum equals to 60. Shrinking. Removed 20 at index 8, sum equals to 40. Expanding. Added 18 at index 13, sum equals to 58. New smallest window found. Indices 9 to 13, length equals to 5, sum equals to 58. Shrinking. Removed 5 at index 9, sum equals to 53. New smallest window found. Indices 10 to 13, length equals to 4, sum equals to 53. Shrinking. Removed 8 at index 10, sum equals to 45. Expanding. Added 22 at index 14, sum equals to 67. New smallest window found. Indices 11 to 14, length equals to 4, sum equals to 67. Shrinking. Remove 12 at index 11, sum equals to 55. New smallest window found. Indices 12 to 14, length equals to 3, sum equals to 55. Shrinking. Removed 15 at index 12, sum equals to 40. Expanding. Added 27 at index 15, sum equals to 67. Shrinking. Removed 18 at index 13, sum equals to 49. Expanding. Added 30 at index 16, sum equals to 79. New smallest window found. Indices 14 to 16, length equals to 3, sum equals to 79. Shrinking. Remove 22 at index 14, sum equals to 57. New smallest window found. Indices 15 to 16, length equals to 2, sum equals to 57. Shrinking. Remove 27 at index 15, sum equals to 30. Expanding. Added 25 at index 17, sum equals to 55. Shrinking. Removed 30 at index 16, sum equals to 25. Expanding. Added 14 at index 18, sum equals to 39. Expanding. Added 7 at index 19, sum equals to 46. Smallest subarray with sum greater than or equal to 50 is from indices 15 to 16, length equals 2. In this variable size example, the window size changes dynamically based on the sum condition, unlike our fixed size example where the window size was always 4. For a variable size window, the complexity depends on the problem. Typically, we expand or shrink the window by moving pointers, and each element is added or removed at most once. This often leads to O of n time complexity because each element is processed at most twice, once when entering the window, once when leaving. However, some problems might require additional computations within the window, which could increase the complexity. Usually O of 1, as we only track pointers and a few variables, like the sum or count. Some problems might require additional space, for example, a hash map for tracking frequencies, which could be O of n in the worst case. The sliding window approach avoids redundant computations. In our fixed size example, we reduced the time from O of n times k to O of n by reusing the previous window's sum. In the variable size example, we process each element at most twice, keeping the time at O of n. This efficiency makes the sliding window ideal for array problems. A subarray is a contiguous portion of an array, and sliding window often works with subarrays to optimize solutions. The sliding window approach can use fixed size or variable size windows, depending on the problem. Time complexity is typically O of n for both types, though variable size windows may have additional factors. Space complexity is usually O of 1, unless the problem requires extra data structures. It's great for problems involving contiguous subarrays, like finding sums, lengths, or specific properties. I hope this detailed explanation, along with the visualizer and examples, has clarified the sliding window approach. Try applying it to other problems and see how versatile and efficient it can be.